Hi, this is Kim Keough. I'm with.
Okay. If we're only going to have a handful of people here, we're going to run this a little bit differently than normal. You guys can go ahead and unmute your mics, and we'll just talk through rather than doing a sort of more traditional fixed presentation. That'll allow us to have more of a conversation. So first of all, good morning and welcome to Hood's very south campus, also known as my kitchen. We are trying to do something very different this year. We have never done anything like this before, so if there are a few hiccups along the way, please be patient with us. I guess I'll start by just, and go ahead, Christina, you can start the recording now. I guess I'll start by just asking if you have any questions, right? So do you have any questions about Hood or about the Department of Chemistry and Physics or anything like that?
At this point, I don't. My son's been accepted. He's interested in chemistry, and I was not able to come to campus. So I thought I'd just sit in and hear what you guys are all about. Okay.
So I'm very glad to hear that you're interested in chemistry. That is, of course, the best major out there. So our department is a department about, it's a department of chemistry and physics. So we have 4 full-time chemists, a half-time chemist, and a full-time physicist in the department. And so we offer both chemistry and biochemistry majors. It varies from year to year exactly how many majors we have. It fluctuates, usually sort of on average, it's about 10-ish majors per year. And the balance between chemistry and biochemistry fluctuates pretty wildly too. One of the things that we very much pride ourselves on is our active learning style of teaching. So we try to do as little straight lecture as we can. And instead try to do more activities and lab-based stuff to motivate what we're doing. And so the intention for today is to try to give you a sense of that in a terrible remote learning Zoom kind of mimic of what we would normally do in lab, which would be by its very nature much more interactive and much more in-person relationships kind of thing. So what we're going to talk about today is the science of color. And in particular, I'm going to do a lab that you may have seen before. It's using our friendly old red cabbage here to look at acidity. But we're going to take it a little bit further than probably that you've seen before. So what I'm going to do is I'm going to start with my handy dandy red cabbage, and I'm going to cut a good slab of that off. And this is literally just a cabbage that my wife bought at the store. And there's nothing special about it. I'm gonna chop it up a little bit so it works better in the blender. And then we throw it in the blender with a little bit of distilled water is the only other thing I'm gonna put in there. You can use tap water. This is actually a lab you can do at home if you've got littler kids. It's kind of a fun one for them without necessarily all the explanation. Okay, so first we put in the cabbage. The one thing you can't get a sense of as we do this is just how wonderful this smells. All right, so we throw in the distilled water. And I'm going to ask my wife to mute this so that you don't hear the blender here.
Thanks. Thank you.
Okay, so now we have pureed cabbage, and all we're going to do is just strain out all the remaining junk. And you can see we get this nice purple liquid coming through. There are instructions out there that have you cooking this or boiling this or whatever. Turns out that's not actually necessary. You can do this pretty well with just straining it. Okay, so there's our red cabbage. And if you have questions along the way about what I'm doing or why I'm doing it or why things work the way they do, just let me know. So I'm gonna take and try to get that, there we go, get some more of that liquid down there. And then we're gonna start just by combining this red cabbage juice with a bunch of household chemicals to see what happens. This is generally one of our students' favorite labs. We use this as an introduction to acid-base chemistry, which we'll talk about in a little bit. In part, it's a favorite because it's so colorful. All right, so got that. Grab another. Oh, let's put this in the sink. There we go. Okay, so we've got our nice colorful cabbage juice here, and we can go ahead and first thing I'm going to do is just take some distilled water and put it in there just as a standard to show you what this looks like with just water there. So if we go ahead and put that in there, you can see we've got a nice purple color. Bring it up a little closer so you can see it. So we've got a nice purple color to the cabbage juice. And putting in distilled water doesn't change that. But if we can go ahead and put some things in there. So we'll start with a fun one, vinegar. Right, so vinegar, we throw a little bit of vinegar in a test tube. And we throw the cabbage juice in. And you can see now, it's a much more reddish color, right? The one on the left, my left, is the vinegar. It's much more reddish, right? And then we can go ahead and throw in, oh, what's another good one? Here's baking soda, right? So if we throw a little powdered baking soda, I'm gonna do this over the sink because otherwise I'm gonna make a phenomenal mess here. Okay, throw a little baking soda in and throw a little distilled water in on top of it so it dissolves. We can see a nice pretty blue color. Right, so this is the comparison here. Maybe I shouldn't have worn a blue shirt today. Right, so you can see the two colors here, right? And here's another, let's see, cream of tartar. Right, so we can throw cream of tartar in. That's another, if you don't do a lot of baking, that's one that's used in making snickerdoodles. So one of the things that I'm a little bit known for at Hood is I make cookies a lot. I basically use cookies to bribe my students to come talk to me. And so there are pretty much always fresh baked cookies in my office for anyone to come and steal, right? So the cream of tartar here, you can see, is coming out sort of halfway between the red and purple, right? It's a much more sort of well, I guess a reddish purple. Yeah, you can tell I'm not an artist. Or milk of magnesia. This is a good one. All right, we can throw some milk of magnesia in. Oops, I need to shake that up a little bit more. So milk of magnesia chemically is magnesium hydroxide. And it's used for, if people have an upset stomach, it's used as an antacid. Right, oh, I already got enough water in there, I don't need that. So we can put a little bit of that in, and that one's a little more sort of on the clumpy side. But you can see that's a nice dark blue color as well. If I can hold it in a way that you can see, it's blue, almost going toward green there.
Yeah.
Right. And well, let's do a fun one here. I have two kinds of vitamin C here. All right. I was kind of surprised when I did this just as a test yesterday. Right. So here's some powdered vitamin C. All I've done is break up the pill so it dissolves better here. Put that in some distilled water. And that one turns that same purple color, very much like the acetic acid did, right? And the other one is just a different brand of vitamin C. Pour that in, same thing, just some distilled water and some cabbage juice. And you can see that turns a purple color. It's a very different color than the other vitamin C is.
Yeah.
So there is something chemically different about those two vitamin Cs, even though they're both sold just as vitamin C. They're both even 1,000 milligrams. I mean, they're one, you can see a little different color in it, but that's completely because they put a colorant in there. So the question here, of course, is what's going on here? What's causing this? So science is not just observation. Science is also explanation, right? If it's just observation without explanation, it's not science. So we have to figure out what's going on here. And I've already made a couple of references to acid-base chemistry. So what we have here is a great example of an acid-base, what we call indicator. So if I grab here, I have 11 test tubes here with different acidities to them. They run pH 1, 3, 4, 5, 7, 1, and then 3 through 11, and then 13. And so if I go ahead and put the cabbage juice into each one of those, and I'll bring these closer to the camera in a second once I get them all filled up. Okay, so grab these. Okay, trying not to drop things, right? So you can see there's a nice range of colors here. It goes from a red on your, I guess that's your right-hand side?
My left, yeah.
Your left, okay. I'm sorry, this camera's really mucking me up with left and right. So we've got red at pH 1, and then it goes to pink, and then lighter purple, and then blue, and then back to purple, and then a sort of bluish green, and then green, and this one may turn a little bit lighter yellow eventually. The reaction that's going on here takes a little bit of time, right? So you get this nice range of colors here. Now, when I say pH, how much chemistry have you had, Matthew?
Matt can't talk.
Oh, he can't talk. Okay.
Myself, college.
College?
So.
Okay. So if you've had chemistry, you probably remember the pH scale, right? Which is based on the concentration of H+ ions, acid ions that we have in solution. But it's what we call a log scale. So this one here that's pH 1 is 1 × 10 to the -1 molar in acid ions, right? And so if you take the base 10 log of that, that's a pH of 1, right? Whereas if we go to 7, right, 7 is 1 × 10 to the -7th molar concentration of hydrogen ions, right? And so if you take the negative log of that, that comes out to be a pH of 7, right? 7 is what we consider neutral, right? So if you were to take pure water, you would think that that would be pH 7, You'll notice when I did our distilled water, it's not actually quite right. It's actually closer to a pH of 6 because it pulls any water that's sitting out for any length of time, pulls carbon dioxide out of the air and forms carbonic acid. And so when it forms that carbonic acid, the pH drops a little bit. So if you were to freshly distilled water with no CO2 around, it would be pH 7. But the moment it's exposed to air for any length of time, it goes down. And then it goes all the way down to a pH of 13 here, which is 10 to the minus 13th molar in acid ions. The reason we use the pH scale rather than the molarity is just the huge range of pHs possible. So we normally talk about pHs between 0 and 14. So that would be a molar concentration of 1 down to 10 to the negative 14th molar. And so it's a lot easier to use a log scale when we're talking about 14 orders of magnitude. It turns out that pHs aren't limited to 0 to 14. So for instance, if you took concentrated hydrochloric acid, which is one of the things that we use to make solutions in chemistry, it's 12.1 molar, which means it has a pH of negative 1.1, right? So it's even possible to have negative pHs. We don't talk about them a lot, but they do exist, right? The fun thing about cabbage juice is I've got the same series of solutions here. I'm going to put in what we call universal indicator, right? So this is something we buy. We buy from Fisher Scientific, it turns out. That's a pH indicator. And so I'm going to put about 4 or 5 drops into each thing. And you can see it doesn't mix nearly as well as the cabbage juice does either. But if you look at the colors here, grab that better. If you look at the colors here, this low range here, pH 1, 3, and 5, all look the same. And pHs 13, 11, and 10 pretty much all look the same. It's probably not really easy to see on this screen. But the range of pH color changes with the universal indicator that we buy is more limited than when we just use the cabbage juice. The cabbage juice actually gives us a better range of colors. It can actually do the high and low better than the universal indicator does, which is kind of interesting.
Yeah.
So we can look at each one of these here and explain sort of what's going on. So for instance, if we look at the vinegar, vinegar is a 5% solution on average of acetic acid, right? So acetic acid, if we draw the Lewis structure, looks like this. When you add it to water, this hydrogen transfers over to the water, giving us acetate ion. And I'm running out of room here. H3O plus is just sort of our prototypical acid, right? So when we're dealing with vinegar and water, that's the reaction that's happening, is you're losing that proton from the acetic acid. But acetic acid is a weak acid. It does not completely dissociate. And so you end up with a pH of about 3, right? If I stop sharing my screen, you can see that. If you look at the color of the acetic acid solution and bring it up to the pH 3, it matches that color almost perfectly, right? So even though this is a 5% solution of acetic acid, its pH is only about 3. And then at the other extent, you've got the milk of magnesia, which has a pH very much of 11, right? That's because the milk of magnesia is magnesium hydroxide. And in solution, magnesium hydroxide breaks up into magnesium and hydroxide ions, and the hydroxide ions pulls H plus out of solution, right? So the question that always comes up that is rarely answered well when this demo is done is actually what's going on? What is it about cabbage that does this, right? And if you look at the explanations online, you'll find, oh, it's flavin, it's anthocyanin, talking about those things as if those were only one thing. The answer is really quite complicated, but it comes down to basically, you have something called these anthocyanins. It's one of the things that we have in, come on. Sorry, I'm having trouble with my computer here. I'm trying to share my screen and it's not wanting to do it. I'm not sure why it won't let me share my screen right now. My apologies, my computer has decided to be stubborn. Okay, I guess I won't show you the PowerPoint. I knew there was going to be something that was going to go wrong here. Oh, there we go. That's how to do it. There we go. Okay, now I can share my screen. My apologies. The technology always works until you try to do things live.
No, no worries. It's fine.
All right, so if we look at, okay, this is the Lewis structure of a general anthocyanin. So this is the thing that we have, or one of the things that we have in red cabbage. There's a bunch of other colorants as well. There are actually a whole series of these. They differ by these two R groups here. You can see there's about six different combinations of these different R groups possible for the anthocyanins. And each one has a slightly different color. Each one has a slightly different change with pH. If you want to see what's actually happening with the pH, if you look here at low pH, you have sort of that structure that I just showed you. But then as the pH gets higher and higher and higher, the chemical structure actually changes. So here you have a double bond between this O and this carbon. And here you've added an OH to there and broken up that double bond. And here the OH is lost and you're left with a double bond there. And there's a double bond to the O here, right? And so each way, each time you change the pH, you get different chemical changes to the structure, including breaking open this ring at really high pHs. Those changes are all reversible, and so when you change the pH back, it'll change back in color as well. So this is only one of the things that's present in red cabbage that gives you that color. There's a couple others, flavins and other things like that as well. So that's the real brief version of what's going on here. All right, so now it's about 10:45 or 10:48. Which is the time they told us we should really stop. But before I do you have any questions? Has this brought up any questions, anything you want to know either about Hood or about the fun chemistry we're doing?
Yeah, Matt's walking out here. He's going to ask you a question.
Okay.
Hey, it's Matt. You said you have about, did you say 10 students that going for a degree at one time? Is that 10 per class or 10 total?
10 per year, 10 per year. So usually it's about 10 per year.
So
freshmen through.
Well, so in your general chemistry class, we have about 125 or so students that take general chemistry, but we take general chemistry and break it up into multiple sections. So every section is limited to 24 students. So your general chemistry class, both lecture and lab, will have no more than 24 students in it. And then when we go, there's a lot of biology students who take it. Anyone that's pre-med has to take general chemistry. People take it just to fulfill the core. There's lots of reasons people take general chemistry. And then when you go into organic chemistry, we have about 40 students that take that class. And then when you get to the upper level chemistry classes, then you're talking class sizes of 10 to 15 to 20, depending on which class it is. Not every class is only taken by chemistry majors, but the class sizes are very small. And that's one of the big advantages that we have, is that with a small class, we get to know our students really, really, really well. And so, you know, when I have someone as a freshman who wants to be a chemistry major in my general chemistry class, by the time they move through our program, I'll have seen them in 3, 4, 5 classes. So I know them really well. And when I'm writing letters of recommendation for graduate school or for a job or anything like that, it's not just, oh, they were, you know, number 3 in a class of 300, right? I can say very specific things about, oh, they did this project and they were really good at this stuff and things like that. So you get very personalized education, and you get to know your professors, because we don't have TAs, we don't have anyone else other than us teaching the classes. We do have some adjunct professors, but you know, it's professors teaching the classes. It's not graduate students, things like that. Other questions?
Yeah. I've seen where it says an ACS accreditation. Could you go through that?
So we do not have ACS accreditation. It's something we have designed our program such that it is based on those standards, but we have not gone through that process in part because they require 5 full-time chemistry faculty members, and we only have 4.5. And so we don't meet that standard. And so, but if you look at our courses that we have, if we look at the requirements for the degree, it is designed such that it can be accredited as soon as we can convince them to let us hire another faculty member or bring our half-time person up to full-time. So it's based on those standards, and we actually have in the strategic plan to get that accreditation. We're moving towards that, but it is not something we have yet. But our degree is designed around those standards.
Does it make it, if I'm an employer looking to hire, is that a big deal or not? Is it more the school name? Is it, what is the?
Well, so if you're looking for a job, you know, name of the school matters. Most employers aren't going to care about ACS accreditation. What they're going to care about is that you went through a rigorous program. Okay. And so the ACS accreditation is a set of standards that show what a rigorous program looks like. That's why we've based our program off of those standards. But I don't know that any employer is going to specifically ask you about that. But we do want to move toward that as we go, just because it's a good way of showing people that we do have a rigorous program. Of course, we do. What other things they're going to look for? They're going to look for an internship or a research kind of experience. And so a large proportion of our students have those internship or research experiences, either working with a faculty member. So I do research with the National Institute of Standards and Technology on laser spectroscopy. So I bring students pretty much every summer down to NIST. We work with their laser systems, and we do research that gets published in chemical journals, right? And those students that work with me have pretty close to 100% record of getting jobs or going on to graduate school immediately after they graduate. Other professors do research with US AMRID, yeah, lots of other places that they do research with. And we also have relationships with companies. We have relationships with a lot of the companies in the area to help get people internships at local places. We have students that have done internships at the United States Department of Agriculture, which is at Fort Detrick. That's about 2 miles away from campus. US AMRID, which is also at Fort Detrick. Fort Detrick is sort of a hot spot for internships and research opportunities.
I was thinking you guys would have a pretty strong relationship with them.
Oh yeah, yeah. One of our adjunct professors for our Chem 100 class is a Hood alum who is working at USDA. Yeah. And so we have ins in a lot of labs through relationships like that. We have a huge number of our alums who work for different places at Fort Detrick. And they take our students as interns pretty much all the time.
Yeah, that's great.
So how does the, let's talk baseball.
Okay, baseball.
Play on the baseball team. They've got a schedule. They got practices, so forth. They're not out of town that much. I mean, comparatively, like the D1 schools are. Is that going to be doable to actually go through the program, not miss labs and so forth, and be on the baseball team? And
yeah, so absolutely. So I went to a small liberal arts college, very much like Hood. I was not a baseball player, but I'm a runner, cross country and track. And so I did 2 varsity sports. When I was a chemistry major, I was actually double major chemistry and computer science. Our coaches know that you are a student first. And so they work very hard with their athletes to work around course schedules. And so sometimes they have more than one practice in a day, right? So if people can only make a morning practice, they'll do a morning practice. They can only do an afternoon practice, they'll do an afternoon practice. They know that you don't get to miss class or lab for a practice, If you have a game, that's a different story, right? You can miss for a game. We work with students at the very beginning of the semester to plot all of that out, make sure, okay, here's your game schedule. Okay, this is how we're going to make that work. So we do that, first week of class, we're talking with our athletes about that. We have a very high proportion of people who are athletes at Hood, and your professors work with you. So it's another benefit of being at a small place is that we're going to work with you one-on-one to make sure that you can get what you need and what you want.
Thank you.
Thank you so much.
No problem. Any other questions?
That was.
I don't have any more.
I don't think so. Thank you so much for your time. That was a great experiment.
All right. My pleasure. So I think your next thing is the Hood Hello, which may already be in progress, but we'll let you go on to that.
All right, great. Thank you. Take care.
All right. Thank you very much.
Thank you.
Bye.
Yep. Bye. All right.
All righty.
All right. Shall we, have you stopped the recording?
Once I can find that button.
I think I can.